Hello, everybody. I'm Jordi Baylina. I'm the technical lead of Ident3 and Hermez. What I'm going to present here is Hermez. Hermez is a layer 2 solution for scaling Ethereum. So the idea is, well, if you have seen in the last month, you have seen that the gas price of Ethereum, so making a transaction in Ethereum is very expensive. This is mainly because Ethereum, like any other decentralized blockchain, has a limitation on the consensus system. So everybody in the network needs to get a consensus of what are the transactions that needs to be processed. And this has a limitation, that these people is around the world. They need to talk with each other. They need to validate all the transactions, and this makes a limit. Currently, in Ethereum, you can do about 30 transactions per second. Maybe with the last gas increase, maybe 35, 40, depending on if they are tokens or so. But this is limited. In Bitcoin, for example, it's about 1,000 transactions every 10 minutes, which is even lower. But all the blockchains has this limitation, and these limitations comes in the consensus layer. With this, with a rollup system, we will explain later how it works. We can put like 2 orders of magnitude. We can go 2 orders of magnitude more throughput of the full transaction. So in Ethereum, in the case of Ethereum, the theoretical limit would be around 2,000 transactions with the current implementations that we have right now. This is more or less what Visa is doing in an average way. So we are quite well, and this gives a lot of hope in Ethereum and in the blockchain in general for scaling and going to the main users. So how rollup works? How these scaling solutions works? Well, a layer 2 solution, a rollup solution, mainly is like a blockchain. So we have we start with a state of balances. So we have this account has this balance, this account has this balance. This gets a state. We can hash all them together with Merkle tree, and we have this state root. It's a hash that represents a current state. With this, we need to process many transactions. And after processing, I don't know, 2,000 transactions, for example, we get a second state. So processing these transactions mean that some of those balances will be increased, some of those balances will be decreased. Of course, these transactions needs to be valid, and then we create this new state. In a rollup, in a layer 2 solution, we are doing that with a regular Ethereum transaction. Now, in an Ethereum transaction, actually what we are doing is actualizing a state. So in a transaction, we are sending them 2,000 transactions in a 2,000 layer 2 transactions in a single transaction. We are processing those transactions in one state, and we create this new state. Okay. This, if we had to do it with a smart contract, this would be very, very low, because we have to get all these transactions, and we need to validate all the transactions. We need to validate that the signatures are valid, that we have enough funds, that we don't have double spends. We need to do all these validations, and this, if we had to do it by hand, with Solidity, this would be very expensive. Okay, so we will see that there is a trick. It's an important trick. That's actually this zero knowledge, or even the optimistic part. We'll see these different ways. There's a trick that we can increase. We can do this validation very, 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 very fast. Okay, so here is where it comes. This total number of transactions. Well, in an Ethereum, we have one block. We have one block every 15 seconds. In each block, we can put 16 different batches. We can put 16 different transactions of this kind, with each one with about 2,000 transactions. So this gives us a total of about 2,000 transactions per second. This is where the numbers come from. Okay, so what's the trick? What's the trick here? Well, here in zk-rollups, we are using what's called Snarks, or if you want, zk Snarks. The important part is not the zero knowledge part, which has no application here. The important part is the S. The S is for succinct. It's a succinct verification. What's a Snark? Well, a Snark is, imagine that you have a program, a deterministic program with one input, and You put whatever, if you put an input, you will have always the same output. You have a deterministic program. This program can be very, very, very expensive in computation. So it maybe in a important computer can take maybe 1 day or 2 days or 1 hour. It can be very expensive computation on this. In the case of zk-rollup, what we are doing this program is mainly the validation. In the input, we have all the transactions, we have the initial state, and the output is just saying, okay, this is valid. So these transactions are valid or are not valid. So okay. So, and the idea of these primitives is that you can compute this. So the person that's a prover, there is one person that just compute this circuit, executes this circuit, but also he not only computes the result, but he also computes a proof that this is a cryptographic number, that with this proof and the result, a verifier can have the warranty that this execution has been done. And the cool thing of this technology is that the verification, so the verifier, they don't need to run all the circuit again. They don't need to go to all the transactions and check that the signatures and everything is valid. They just take the result, they just take the transactions, they say that's valid, and they are sure, they have the certainty that this transaction, that this circuit was executed right, that's valid. And this verification, it takes very few milliseconds, no matter how big is the circuit. You can validate thousands, if not millions of transactions, at least theoretically. Generating the proof can be very cost expensively, but once you have this proof, validating all this, verifying that this result is valid, it takes just very, very, very few milliseconds, which is something that's very cool. And this is what we are doing here. Okay, so in the case of the here in the transaction, so we're just sending the transactions, and we are validating, generating this proof. So in the transaction, in the block transactions, we are putting the transactions, we are putting this proof, this zk-snark proof, and then the new state, it's consolidated. We go to the next batch, and we are advancing, and we are doing 2,000 transactions per batch, per L1 transaction. Okay, so the other part is for this to work is not enough to send the validation proof. We also need what's called the data availability. We need to send actually the transactions. We need to reconstruct. We need to be able to rebuild the state. So we need all the transactions. We need to put them on chain. We don't need to validate them because this is validated with the zero knowledge. This is validated with the zk-snarks, but the data needs to be available. The data needs to be on chain, needs to be somewhere. Actually needs to be available. The only thing that needs is that if somebody wants to know what's data, what this state, what's the current status, that you need to be available. You need to be able to compute that. Okay, so here there are different approaches. In rollups, mainly what we do is just put this data on chain. So we send it with the transaction, so we know that this data is available. But there are other kinds of strategies. For example, we can put it in a federation of servers. Okay, so and as far as there is one server that serves this value, that the data is available, then the system will work. So with this will have the map of different rollups, and these are the names that you may have seen in different places. We have two kinds of validation methods. One is the snark proof, which is what I explained to you. There is another method, which is the optimistic rollup. The idea of the optimistic is that you just send the new state and you don't prove anything, but the state is there. And the idea is that somebody can challenge this proof, and the coordinator, if they are not doing the things in the right way, then they lose some kind of collateral. So you have the coordinator has a collateral money there. The people just challenge you, and if you are not able to prove whatever to solve the challenge that is making to you, then the coordinator will lose some money. This is what's about optimistic rollup. The optimistic rollups that requires this game theory, this challenging system. With zk-rollup, this is much easier. You just put the information, you put this proof, and you don't need to challenge anything, because this proof actually guarantees that the current state is valid. And this is the cool thing of rollups, and it's very fast. You don't need to wait for this challenging period, so have all these advantages that with this. Okay, and the other division is about where this data, this data of transactions is stored. If you store that in the on-chain, then we call it a zk-rollup. If you are storing this data in other servers, then we call it Validium. Okay, but it's like just in the on-chain, you just put the proof, you just have the hash of the state, but all the transactions that goes from one state to the other, they are stored somewhere else. Okay, so in Hermez, what we are building is a zk rollup. Okay, so this is how the rollup, as I mentioned, how the rollup circuit, or if you want this verification proof, what we are verifying? Well, actually we are processing transactions. Okay, so we have an initial, an old root here. We have so the current state. We process 2,000 transactions. We have intermediary states on it, and at the end we have a new root. So for every batch forge that we have in a rollup, we have an initial state, we have a final state, and the proof that validates this. Okay, and then, as I mentioned before, in this circuit verification, we have to verify the signature. We have to verify that the state is actually in the current states, that we have enough funds. So we have all this verification is done inside the circuit, inside the process transactions. Okay, but okay, the question is, and who is the operator? Who actually computes this huge proof, and who actually has the possibility of updating the state, of processing the transactions? What would be the miners, if you want, for if you think in the layer one simul? Okay, so who's the operator here? Okay, there are different systems. In many systems, they are just decentralized. Sometimes decentralized is just a single operator that just forces that. This has a lot of inconvenience. Okay, but in Hermez, what we have a decentralization system. It's in Hermez, everybody should be able to be an operator. And how do we select who is the operator? Well, actually, what it is an action. Okay, an action. To be an operator, you need to participate in an action. And the operator that's willing to pay more for a slot is 40 blocks, which is 10 minutes. The one that's willing to pay more, that's the one that will be where the slot will be assigned. And during that 10 minutes period, during that 40 blocks period, the operator can forge as many transactions as he can. He can send many transactions, each transaction with 2,000 transactions, so he can, and he has an incentive to put as many transactions as he can, because he's getting all the fees of all these transactions that's proceeded. So he will have to compute this. Okay, how much cost does what are the costs of running the operator? Okay, what's the cost of this of the gas of the layer one transactions and so on? How many transactions are in the back pool? So what are the income? What are the benefits that I will get currently? So here I can put a bet, and if the best one will be the one that's the winner, and then this one will be able to beat on that. In order to solve some initial possible attacks, people for example, some attacks of buying the slots, but without forging any transaction, just to attack the network, maybe from competitors or so. We divide the 1 hour in 6 slots, each one 10 minutes, and we have we have 6 kind of slots, and for each kind of this kind of slots, we can set up a minimum bidding. Okay, and so it's possible that at the beginning we have maybe half of them that would be like free. Anybody, this minimum will be very low, so it will be anybody can meet, and the others, they have different values, different fee values. Okay, so have this mix of so some of those lots will be more decentralized, some will be less centralized. In Hermez, as I told you, we are building a full decentralized system, a full censorship resistant system. And the idea is to have to minimize governance. We want the system to run as with less governance as we can. Ideally, we want to avoid any decision making on the governance. Okay, so that's the idea of governance. At the beginning, it's going to be a little bit centralized because there is some security things, but we will go decentralization as the system goes running, and we hope that in very few months this will be fully decentralized. Okay, you can. One of the questions that may come to you is, okay, what happens if the coordinator does not want to forge my transaction? Then what happened with my coins, with my tokens that are inside the rollup? If we want a censorship resistance, we need at least a way to exit that. Well, with Hermez rollup, actually what you can do is with a layer 1 transaction, you can do what we call a force exit. Force exit will force, so that means that in the next coordinator, in order for the next forge to be valid, these transactions needs to be forged, needs to be included. Okay, so with this we guarantee that in the coming forge, these transactions will be processed. Okay. If there is like an edge case, that is, if there is no coordinators that forge, then there is like a kind of a timeout, and then it's the system enters in a state that anybody can forge a block. So even if nobody's forging, you can forge yourself your forge your block, and you can exit the fund. So the system will the system will guarantee that you will always have your funds available when you want. Okay. Another property of the Hermez rollup is that we are also allowing what we call atomic swaps. Atomic swaps. This is a very interesting for decentralized exchanges. An atomic transaction is mainly it's a transaction that in order to be valid, maybe another transaction needs to be forged. So in the case of exchanges, for example, I'm sending to you Ether, but this transaction is going to be valid only if you send me back DICE. Then you can build an exchange on top of these atomic transactions. Okay, so this is fully included in the first version of Hermez. Hermez, as I told you, Hermez is developed by the Eiden3 team. In Eiden3, we developed many of the zero knowledge tooling to build for building all kind of applications, privacy applications, but also scaling applications like the rollup. We are the authors of Zircon. Zircon is a language to build this deterministic program that needs to be computed, needs to be very special. Circumlib is a library of standard components like signatures, hashes, and some standard components used in Circum. Snarks.js is an implementation, a fast implementation in JavaScript, where you can prove and verify the zero knowledge, the Snarks, the zero knowledge proofs. We have Rapid Snark. Rapid Snark, this is quite new, but this is a CPU implementation, very fast CPU implementation. Actually, we are twice as fast as the best prover that that exists until now. It's fully all this tooling is absolutely open source, so anybody can use it. And this works in an Intel. It has a lot of assembly code, and it's very optimized. And with this, we can generate, so as a reference, we can generate 128 million constraints in less than 2 minutes, which is very good. And yeah, well, different tooling here. Okay. So that's mainly my presentation. Just to wrap up, is we have an implementation that is able to handle 2,000 transactions per second. It's fully decentralized and censorship resistant, has atomic transactions. We are lowering the transactions. We expect that the cost of the layer 2 transactions will be under like 1/10 of the current gas price. Right now, we are in a public testnet. We will announce during this week the public testnet. We hope to go mainnet in the upcoming maybe 2-3 weeks. We are just doing all the stress test right now. We are very excited to launch it. That will be just very soon. We're finishing the trusted setup. We have run 3 different independent audits of the smart circuits. Everything is open source. You can check in there. So yeah, let's go to scale.